Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll discuss the simplest statistical models we could examine using the framework from Chapter 1 of your textbook and describe measures of central tendency and variability in terms of this framework. These slides correspond to material in Chapter 2 of your textbook. Before we dive into the material, I want to provide you with a few tips on how to best use the material in this lecture. This is your first introduction to some of these formulas, and they are also in the book. You will need to know these formulas and use them for calculations in class, so I highly recommend taking notes while viewing these lectures and making sure you understand each formula. To this end, if some of the slides move too fast for you, pause the video lecture and take your time to absorb the information from each slide. If the material is confusing, your book covers the same material and is a good second source. As always, you can always ask me questions during the quizzes for each week for clarifications on anything that you're not sure about. To start this lecture, I want to clarify a few definitions to avoid confusion. So we want to talk about the distinction between estimands, estimators, and estimates. An estimand is a population parameter we are interested in making an inference about. For example, the mean estimand is mu, the population mean. An estimator is the rule for calculating an estimate of that population parameter based on our observed data. For example, the mean estimator formula is the sum of scores divided by the total number of scores. Finally, an estimate is the result of that calculation. For example, the sample mean might be 5 in our observed data. This is an estimate of the population mean. Now that we're clear on those definitions, let's continue with our data analysis framework. The very simplest model we can specify would be to have a single parameter estimate B0. B0 is some constant calculated from our data, and then we have individual error values for each person. This simplest model, or a model with just a single parameter estimate, is the model that we're going to be working with today. Let's look at how we might calculate some familiar statistics using this framework. We know that y sub I are the data points. Here are 5 raw data points. When we talk about estimating the parameters, we mean it in the sense of estimating from a population to a sample, not statistical estimation. We're not there yet. Our mean, median, and mode are estimates of central tendency in the population distribution, but are calculated from our sample distribution of scores. In the simplest model, B0 is a single value giving us information about the center of a distribution of scores, the definition of a measure of central tendency. This framework that we are working in, our data analysis framework, does not distinguish these central tendency estimates from the estimates we get from more complicated models. This differs from how you may have learned about stats to date, where distinctions are made between inferential and descriptive statistics. Let's work with the mean value for a minute. We know how the mean is calculated, by summing each score and dividing by the total. Each score on y has an associated error we can calculate, the difference between the mean and the raw score. One way to calculate the error would be to subtract the score from the mean. This would give us the error values in the column on the right. There's an error score for everyone, but we also would like to know about the summary error, a single value for error that best represents error for everyone in the data. What your book describes as typical error are measures of variability such as the variance and standard deviation. In our data analysis framework, we call these measures of typical error. When we are trying to choose a beta or estimate a parameter, we are trying to make the summary error as small as possible. Let's talk about how we can get summaries of error. First, we need to aggregate or combine the error values to get some measure of total error. We can do this in a variety of ways. We could do this using a count of errors. In a count of errors, we would simply count whether an error occurred, but then we wouldn't have information on the size of the errors. A way that we could do this is to create a binary count error variable where if error equals 0, the count equals 0, and if error does not equal 0, then the count equals 1. I'll give an example of this in a minute. It would be better than just counting the errors. It would be better to sum the actual values so that the values are taken into account. But if we do this, obviously positive and negative error values would cancel each other out. So this isn't a great solution either. This would be summing the error values. We call this the sum of errors. So since we don't want the positive and negative error values to cancel each other out, we could take the absolute value of each error value and then sum them. And this is what we do with the sum of absolute errors. We remove the sign from the error values and then we sum them. And this is definitely better than just the plain old sum of errors or the count of errors. But with the sum of absolute errors, then we are assuming that there is a ratio value to the error scale. For example, 4 error values of 1 would equal an error value of 4. But a lot of times, we consider bigger values of error to be significantly worse than the small ones. So we want to add some sort of penalty to the larger errors so that they contribute more to the error summary. This brings us to the sum of squared errors. We can square each error value, and this both removes the sign of the error, and the larger errors contribute more to the error summary. The sum of squared errors is the most commonly used aggregate error index. And then finally, we can add weights to the squared errors if for some reason we think that certain observations should contribute more to the summary error. The most commonly used aggregate error indices are the count of errors, the sum of absolute errors, and the sum of squared errors. And these are the ones that we'll focus on for the duration of the lecture. So you have a choice of which aggregate error index you use. Those are the ones that I just went over. But it's important to realize that the aggregate error calculation actually influences the calculation of B0. Each aggregate error index has a corresponding estimator that will provide the best estimate of B0. Remember that estimators are rules for calculating estimates of population parameters. So these estimators and aggregate error index pairs go hand in hand. You are familiar with these estimators because they are all measures of central tendency that you've seen before. So the best estimator when using the count of errors is the mode, the most frequently occurring score. The best estimator when using the sum of absolute errors is the median, the middle observation of all scores. And the best estimator when using the sum of squared errors, which is most commonly used, is the mean, or the calculated average of the variable. Your textbook gives a proof showing how the mean is the best estimator for reducing the sum of squared errors in the simplest model. Let's look at how these types of errors are calculated with their best estimators using the previous example. We know the best estimator of B0 for the count of errors is the mode. So the mode here is highlighted in blue. The column under the plus sign uses the mode to calculate the difference between each score and the mode. The count of errors only counts whether an error occurred. So the count of errors codes the values in the column under E sub I as being 0 or non-zero. So we have calculated these errors here, but then we code them as whether they are 0 or non-zero. Here, 3 out of 5 scores had non-zero error, so the count of errors is 3. You can see that in the column all the way to the right. For the sum of absolute errors, the best estimator of B0 is the median. The column under the plus sign uses the median to calculate the difference between each score and the median. In this example, the median and the mode are the same, so we have these differences calculated the same in this example as they were in the last example where we used the mode. The sum of absolute errors takes the absolute value of each calculated error and then sums them. In this example, one error score is -5, so the absolute value of this is 5. The others are all absolute values of positive scores, and so they remain the same. We sum all of these absolute value error scores to get 1 plus 6 plus 5 is equal to 12. So the sum of absolute errors is 12. For the sum of squared errors, the best estimator of B0 is the mean. The column under the plus sign uses the mean now to calculate the difference between each score and the mean. Then each of those calculated differences is squared. Squaring them both makes them positive and gives more weight to those larger errors. For example, we can see here in the column all the way to the right that there are 2 relatively large errors in opposite directions for the scores 14 and for 3. Those are given more weight and are similar in size because they are similar distances away from the mean. Summing these squared errors gives a sum of squared errors of 61.2. This concludes the first lecture on types of error and estimators for each type of aggregate error. In the next lecture, I'll continue describing measures of typical error.